So what we just did in those exercises, basically think about voltage in terms of what is the voltage at a location in space. Now, if you put an actual charge at that location, then that charge would have a voltage and it would also have a potential energy. But we're going to back away from that a little bit and we're going to talk about instead the idea that if you had two charges, would they have potential energy stored up between them? Like, for example, I had a positive charge in my left hand and a positive charge in my right hand, and they're this far apart. Would there be potential energy?
Yes.
Yeah.
How come?
Because they're both positive.
Because they're both repelling each other, right? And if I let them go, what would happen? They go flying apart. What if I had three positive charges in a triangle? Charge, charge, and charge. Would there be energy stored up?
Yes.
Absolutely. What if I had three negatives? Charge, charge, charge. Would there be energy stored up? What would they all want to do? Attract to each other, right? Oh, sorry. No, they would want to repel. What if I had a positive, and a negative? Would there be a potential energy associated with that?
Of course.
Yeah, because there would be a potential energy between these guys, a positive potential energy trying to repel them, then a negative in between here and here trying to attract them, and a negative between here and here trying to attract them. So what would the total potential energy of this whole triangle be with two positives and one negative? Wouldn't you have to figure out the potential energy associated with each pair?
Yes.
Okay, so if you have three charges, how many calculations would you have to do?
22.
1, 2, 3. If you had four charges, how many calculations would you have to do?
No. Yeah, 4.
Say 1, 2, 3.
4 times 3 times 2.
6.
4 times 3 times 2? No. I like the way you think though. It's 4 plus 3 plus 2 plus 1, which is 10 calculations you'd have to do. 5 charges, how many calculations would you have to do? Yeah. So anyway, you could draw the little diagrams or you could do the math behind it. But the point is, it grows a lot when you start adding more charges. Just back to that idea I showed you earlier with 100 charges. It's like a ridiculous number of calculations you have to do. Does that make sense? All right, so here we go. Potential energy stored between two charges is really easy. It's just KQQ over D or negative KQQ over D, right? But what if you have more than two charges? Well, guess what? You've got to do between these two, you've got to calculate that, you've got to calculate that, and you've got to calculate that. The total potential energy is the sum of those three. And if it's repulsive, it's a positive potential energy, and if it's attractive, it's negative potential energy. Sound good? All right, so we're going to play a little game. I'm going to turn the lights on, and I need 4 volunteers. 1, 2, 3, 4. Come up to the front of the room. I can't remember if we've done this before. Have we done this before? I got 2 volunteers. I need 2 more. All right, one more. Okay, here comes Trina. All right, here we go. So, as the people in the audience, your job is to judge. People up here, your job is to perform. Now, if you look at these people up in the front of the room, and you look at their faces, would you consider them very positive people or very negative people?
Negative.
Very negative. Clearly very negative. Look at that. Look at that smile.
Yeah, Justin's very negative.
All right, very negative. And now if you're all negative people, what's that all mean?
Everybody wants to get away from you.
You hate each other. You hate each other. Go. Go. And when I say freeze, you have to stop moving. Oh, good question. If they were all positive, they'd still hate each other. Right. Yeah, so freeze. Take a look. People in the audience, what did you agree or disagree? Agree. Where'd they all go? corners of the rooms, right? All right. So we're going to shuffle you guys around just a little bit. Instead of going to the corners, we're going to go, let's see, James, you go to the middle of that room. You go middle there. You go middle there. And you go to the middle of the wall. Okay, so instead of having people at the corners, we now have people in the middle of the walls. All right, take a look. If, for the members of the audience, is this situation more or less, how do I say this?
Better or worse?
Likely.
Which is more likely, corners or sides of the walls? Why corners? Because they're further away in the corners? Or are they further away in the corners or are they further away in the sides?
It's a normal question.
Corners or sides? Which is further away? Are you sure about that? Okay, I agree. All right, everybody. So Natalia is like beating me over the head with this. She's absolutely right. Okay, come on back. Nice guys. Nice job, guys. You're neutral now. You can exist without being repelled. So, yeah, it turns out this is that age-old question. Why does anything happen in the universe?
For reasons.
No, there's a reason. Because things are lazy. Things always like to go to the lowest energy state, right? So if everything's repelling everything else, which is the lower energy state? Closer or farther?
Farther.
Farther. All right, so what we're looking for is we want to actually calculate the potential energy associated if everyone was on the side of the walls, in the middle of the walls, or if everyone was in the corners. So we're going to actually compare those two numbers to see which is the lower energy state and by how much. Sound good? All right, so here we go. Scenario 1, we're going to go put people in the sides of a square room, or by people I mean electrons. All right, so if electrons are in the side of the room, that means there is a force between these guys. So there's a potential energy between these guys, potential energy between these guys, potential energy between these guys, between here and here, between here and here, and between there and there. Wouldn't you agree? So 6 of them. So 6 calculations you have to do. This length, if these are side length 2, this distance is 2, and this distance is square root of 2, right? All right, so the total energy between all of the charges is, let's see, this guy is KQQ over root 2 d. This is KQQ over root 2d, KQQ over root 2d, KQQ over root 2d. How many of those do we have? 4 of those. And then we have KQQ over 2d and KQQ over 2d. How many of those do we have? 2 of those. So total, we've got 2 KQQ over 2ds and 4 KQQ over root 2ds. And if you simplify terms, it's 1 plus 2 root 2 KQQ over d. I forgot to write the d, I apologize. There's supposed to be a d there. Good? All right. Next, corners. This is 2, this is 2, this is 2, this is 2, and this is 2 root 2 and 2 root 2. Agree? So you do the math, you end up with 2 plus root 2 over 2, which is a bigger number. 1 plus 2 root 2, or 2 plus 2 root 2 over 2, which is bigger. Turns out, scenario 1, the energy is bigger. It's about 3.8 KQQ over d. Whereas in scenario 2, it's about 2.7 KQQ over d. So where will the electrons actually go? The corners. All right, and that is the math behind it. Scenario 2 wins. So, one of the rules is that charges accumulate in sharp points. Are you aware of this? Do you remember this from last year? If you have a charged object, charged metal object, let's see, I need a charged metal object. Here we go. Scissors. Hold out the scissors. If I were to charge up these scissors, where would the charges naturally accumulate?
To the points of the scissors.
Tips. Why?
That gets the lowest energy state.
Because that gives you the lowest energy state, right? Right? It's lower energy to have a bunch of charges at this point and a bunch of charges at this point than to have the charges distributed evenly along the sides. Does that make sense? All right, and things will always go to the lower energy state. So, is that it? Let's see. Which configuration gives the lowest average voltage? Huh. That's interesting. What's voltage again? Do you guys remember? Potential energy
over co-charge.
per charge. So which situation gives you the lowest average voltage? The second situation. So when this thing has come to equilibrium, the equilibrium position will be scenario 2. Voltage tends to distribute itself as evenly and as lowly as possible, such that a conductor in an electrostatic equilibrium has the same potential energy per charge everywhere, the same voltage everywhere. They all have this, the one on the right has lower potential energy with same number of charges, therefore lower voltage. So that's the situation that will occur. Does that make sense? All right, I think that is it.
I like the note at the end. Is this not cool?
This is very cool.
Are you not entertained?
Oh my gosh. All right, and that is it. Nice job, guys.